by just kind of reviewing what we talked about. And really, this is just applications of Newton's second law mainly. It's just applications of Newton's second law in a slightly different way. So as we all know, Newton's second law simply states that the net force acting on an object equals that object's mass times its acceleration. These are vector equations. But when we start applying that to uniform circular motion, then we can make some modifications. So some caveats when we're talking about uniform circular motion. We are talking about motion in a circle at constant speed. And even though it's speed, we still use the symbol v. And constant radius, and that just, constant radius. Really, you can't have, can I spell radius? You can't have circular motion unless you have a constant radius. If the radius changes, you're not traveling in a circle, right? And just so you know, you will expand on this if you go, especially if you're going to go into like astrophysics. You're going to be one of those crazy smart people, right? Circular motion is where you start because it's the easiest one. But then there's other types of curves, right? You have hyperbolic curves, you have elliptical curves, you have straight lines, you have points, which you could just be at rest, right? But you start with straight lines and being at rest, and then you go to circular motion because circular motion is easier because things don't change. But then you go to like elliptical motion, where you have changing speeds and changing not radii in that case, it's foci in that case. The foci of an ellipse. Do you ever learn about that yet when you did geometry? Did you do ellipses at all? No. Well, you'll learn conic sections in the future, and you'll do it there. But this is the starting point to studying curved motion. So yeah, constant radius, constant speed v. Okay? Now, if we are traveling with uniform circular motion, then we have a center-seeking or centripetal acceleration, which is equal to the speed squared divided by the radius of the circle in which the object is traveling. And again, we will prove this in AP Physics C next year, or if you're like Joel and you're going to take calculus-based physics in college, you'll do it there. But this is only true if these two things are true. Okay? And then we also learned that, well, just using good old distance over time for speed, like we did in middle school, if I'm traveling in a circle, perfect circle, then I can say, well, the time that it takes to travel one circumference, which is 2 pi times the radius of the circle, divided by what we defined as the time period, the period t. Right? T is the period, and it is the time required for one complete revolution. You guys remember that, right? All right, now with these, obviously, see we have a v here we have an acceleration in Newton's second law. Well, if we have a centripetal force causing centripetal acceleration, then we can plug v squared over r in for the acceleration. And then if we know the radius of the circle and the period, the time it takes to go around exactly once, then we can plug this expression in for the speed v there. And so that's how we can deal with the new types of problems when we're dealing with circular motion from the starting point of Newton's second law, which we've been using for weeks and weeks now. Years, it feels like, right? Okay. Any questions about that? Now, this is general uniform circular motion. So this is anything that's traveling in a circle at constant speed where the circle constant radius. But we have started this unit by focusing on orbits, so circular orbits. And I'll point out again, no orbit in the universe is circular. No orbit is. Even the most circular-ish orbits are still slightly elliptical because the conditions required for a perfectly circular orbit are perfect and just don't exist in nature. But you get really close to circular orbits. And again, elliptical orbits or hyperbolic motion where you're moving so fast that you will never orbit, you'll just curve around something and then just continue on your way, it's more difficult. So we start with circular orbits and then you learn how to deal with the more complicated orbital trajectories or motions in space. So with circular orbits, when we start with Newton's second law, if we're talking circular orbits, then our net force will be centripetal and our acceleration will be centripetal. Well, in the case of a circular orbit, our net force is simply the gravitational force exerted on the smaller object by the large object. And if we make this substitution for acceleration, the and let's just use the Earth let's use the Sun and the Earth. So the gravitational force on the Earth will be the mass of the Earth times the centripetal acceleration of the Earth. But we can always substitute mass Earth. We can always substitute the Earth's orbital speed squared divided by the orbital radius of the Earth. So this is Newton's second law. Using Newton's second law, we get this expression for the gravitational force acting on the Earth. But we also have this equation, mass Sun, mass Earth, divided by the orbital radius squared. We also have Newton's law of universal gravitation. And so we can set this equal to that, right? If A equals B and A equals C, then B must equal C. So we can set these two guys equal to each other. And do some simplifications. We did this yesterday. I'm just kind of, reiterating the point. The Earth's mass cancels out, which is very significant. That says that the speed that the Earth must travel based in its location in its orbit the mass of the Earth doesn't matter, right? The Earth will have an orbital speed at our distance from the Sun, but so will a grain of sand. A grain of sand at the distance that the Earth is from the Sun must have the same orbital speed in order to maintain a circular orbit. Literally, the mass cancels out. Literally, the mass has no bearing on that physics. And then we also have, remember, both terms in this equation brought mass to the party. Both terms brought radius to the party, but only one of these guys gets canceled. So v squared is by itself. We just square root that, and we get the equation for the orbital speed, circular orbit. The speed needed to be in a circular orbit, a distance r away from the object being orbited, is simply big G, the universal gravitational constant, times the mass of, in this case, the Sun, but whatever's being orbited, that's what you put in there, divided by the orbital radius. Okay, this is not on the formula sheet. I'm not going to say you're going to need it on the AP exam. I have seen it once or twice on past AP exams. So this is on the formula sheet. Newton's second law is definitely on the formula sheet. So you can always get to this using your knowledge of the other equations. Okay? Cool beans? All right. One other thing I want to show you. Because since we're dealing with orbits, I think this is your sensation of what I'm about to talk about is not due to orbital motion, but I think using a simulation for orbital motion kind of makes it a little more obvious. But I've been talking about centripetal forces, centripetal acceleration, centripetal forces. Centripetal meaning center seeking. Okay. Centrifugal forces, you probably have heard that word. You probably heard of centrifuges, right? That's what they use. They put the test tubes in to separate the blood, the components of the blood, by just spinning them around. They put astronauts in centrifuges and spin them around in circles to make sure they can withstand the G's required to get in space. You ever seen that? Jet pilots do that too. They sit in those rooms and they just spin around like this, and you see their faces go back like that. It's kind of like those rides in the carnival where you stand up against the wall and they spin around and you get stuck to it, kind of like that. So when you're in one of those rides, you feel like you're being pushed out, right? You feel like there's a force that's pushing you out. Whenever you're driving your car and you turn to the left, you feel like you're being forced out to the right. Okay, that is what's referred to as a centrifugal or centrifugal force. It is not a real force. It's not a real force. The reason that there's a sensation of a force when there's not one is because the reference frame that you're in, i.e. the car, is accelerating. And whenever you make measurements from an accelerating reference frame, you always notice things that aren't actually there. Okay, A non-accelerating reference frame, by the way, is called an inertial reference frame. And so measurements made in inertial reference frames will give you what you'll always see real forces. You always see actual forces. But anytime you're in a reference frame that is not accelerating, or that is accelerating, you'll always see these weird forces that don't actually exist. And a good example of that, let me actually, before we get to the simulation I'm going to show you, a good example of that is, hopefully you got all this down. If you're in your car, so here's my picture of a car, and then you hang something from the ceiling of your car, and then you slam on the gas. What do you see this thing do? What do you see it do that? While you're accelerating. As soon as you start traveling at constant speed, it goes back down. But while you're accelerating, this thing goes back. So in the reference frame of the car, the only way to get Wilbur here to have an angle like that is for me to actually exert a force on it, right? I have to push on it. I have to push on it in order for it to do that. If I let go, it just goes right back down. So if I was to draw a free body diagram here, I would say, well, there has to be some kind of force pushing this way in order to have that happen. We know that there's no force doing that, right? That is a fictitious force. I feel like, or the object feels like there's that force because it's in an accelerating reference frame. Or if I put coordinate axes in here, my coordinate system is accelerating. And if it's accelerating, then you always notice these fictitious forces. They call them fictitious forces. It looks like there's this force, but there's not actually that force. So for the same reason, if you're in something that's spinning, or if you're taking a turn, you feel like there's a force, a centrifugal force or centrifugal force, but it doesn't actually exist. The reason you sense that there is one is the same reason that you sense the object senses a force that pushes it back inside the car. It's because if you're turning, you are accelerating. That's another way to definitively say, if you're turning even at constant speed, you're definitely accelerating because you notice these fictitious forces. Okay. So what's really happening, and I'll give you a visual that will kind of tie this together. What's really happening when you turn in your car and you feel like you're being forced out the side, what's really happening is Newton's first law is at play. You're an object in motion. You want to continue with straight line motion, right? So if I'm going to turn to the left, my body wants to keep going straight. It wants to keep going straight. I turn to the left, the car turns below me, and then the friction on my seat, from my seat and my back on me, and then if I'm in the passenger seat and I get pushed up against the door, those forces are actually pushing me this way in the direction that I'm turning. They're the centripetal forces acting on me. And because of Newton's third law, those forces acting on me that are preventing me from traveling in a straight line according to Newton's first law, according to Newton's third law, the forces that push on me, I push on the door and the seat with the same force but in the opposite direction. So it's not that there's a force that's pushing you out. You're actually pushing in that direction in response to the door pushing on you towards the center of the circular arc that you're traveling in. Okay. So it sounds kind of complicated, but no one says in normal conversation, no one says centripetal. Everyone says centrifugal or centrifugal. You'll hear that a lot more in colloquial language than you will centripetal. But centrifugal forces literally don't exist. And so I made this little simulation to relate that concept to orbital motion and to maybe make it a little more obvious. So here I have a star, I have a hollow planet that I've then put a smaller object in. Now what's cool about algodo, I can make this guy and this guy not interact. I put these guys in different collision layers, the little ball inside the hoop, and then the star. I made them on separate collision layers, so this guy doesn't feel an attractive force towards the sun, but the hoop does. So the hoop's going to be orbiting the sun. But this guy's not going to be orbiting because he's not feeling the attractive force. And if I delete the hoop, then that ball is just going to travel out in a straight line. Right? It's just going to move in a straight line according to Newton's first law. But if I have this hoop that's orbiting, this hoop's going to orbit, and that guy's trapped inside, well, that guy still wants to move in a straight line. Well, what's preventing him from moving in a straight line? It's the normal force from the inside here that's pushing this way, right? And we can see that as it orbits. Right? And as soon as I delete this guy, he goes off in a straight line. Right? But if I don't delete that guy, then he traps him in the orbit that he's traveling in. And the force that's preventing this guy from just flying off in a straight line is the normal force exerted on it. And that normal force pushes, ignore the gravitational force there, that normal force is pushing on this object towards the center of the star. And in response to that, and according to Newton's third law, since this object exerts a force on this object in that direction, this object then exerts a force on this object in that direction. This force right here is a real force, but it's not a force on the object pushing it out. It's literally the object pushing on the object that's pushing it inward, right? It's a reaction force. So that is what you feel like is a centrifugal force, but it's not a real force. This is a force, but this isn't a force on you that's pushing you out towards the outside. Centrifugal is actually, centripetal is center seeking, centrifugal is center fleeing, right? That's why it's not real. Okay. That's just a conceptual idea you want to understand on the AP exam that is brought up fairly often, so just keep that in mind. All right? Any questions about any of that? That's my spiel for today, so you can have the rest of the period to work on your quest assignment. Oh, sorry, one other thing. You guys heard of Kepler? Did you ever learn about Johannes Kepler in school? Oh, you should have. One of the smartest people. This is before Newton, before modern science, essentially. His predecessor, a guy named Tycho Brahe, or Tycho Brahe, depending on who you ask to pronounce it, came up with Kepler's 3 laws of planetary motion. When you take Physics C next year, we'll cover those. But before Newton, before calculus, Johannes Kepler figured out his 3 laws of planetary motion. The first one is that planets travel in elliptical orbits. Like he just looked at reams of data that other guys took, Tycho Brahe took, of the locations of the wandering stars, which we now know as planets, and he worked out that the orbits of those are ellipses. Think about doing that several hundred years ago without modern technology. It's incredible. I won't get into the second law because it takes a while to describe. But Kepler's third law of planetary motion says that the period of an object that orbits the sun, he worked this out for like Jupiter and Saturn and Venus and the Earth. The square of the period is proportional to the cube of the orbital distance. This guy worked this out hundreds of years ago, before Newton, before calculus, long before modern technology. He worked this out, and this is true. The square of any object in a circular orbit, the orbits that he was dealing with were highly circular, is proportional to the cube of the distance. Why that was, he didn't know. It took Newton's laws to figure it out. And you're actually going to do that in number 7 on the quest assignment. You'll actually end up deriving Kepler's third law, or at least the mathematical version of Kepler's third law, which is kind of cool. All right. That's it.